This will be the second part of the video, introduction to the Stokes and Divergence theorem. So let me this part it will be about the Stokes theorem. So let me remind you of this fundamental theorem of line integral for vector fields. Okay, it's stated there, and if what you're looking at left hand side is the scalar function and the difference of the values of the scalar function, and b and a, that's the context. One way to look at the theorem is the left hand side involves only the values at a and b, and c is any curve that connects these 2 points. Then it turns out if you bring that inside the integral, then you can write it in the following form: the line integral of a vector field, which is a gradient vector field of the scalar function. So values become the same. And if you think about the meaning of this line integral of the vector field, that's usually interpreted as a work done by the force field. And what this one says is that the work done by this force field, if it is a gradient vector field of a scalar function like this, doesn't matter how you go from here to there, it's going to be always the same. Because the left hand side, it's just about the n values. So if you look into the proof of this one, which is basically just a chain rule and together with the fundamental theorem of calculus, so that part is not that mysterious, but if you interpret it as this work done by this force field, it's quite interesting that however you arrive from here to there, the difference is going to be always the same. So for that region, this f is called a potential function, and then it's a potential energy of, for example, gravitational field and those things. So this will be generalized. This type of phenomenon will be generalized. Let me first remind you of the Green's theorem. So here's the Green's theorem. The Green's theorem is happening in xy plane. So this R is the region, and C happen to be the boundary of this region, and all happening in xy plane. Then you can look at this as a vector field, not necessarily the gradient vector field, an arbitrary vector field, and a P and Q. So I wrote it in there. This is the expanded version of this vector field dotted with the velocity vector. So for example, if I have this C, there's not much of a choice for this R part. R is if it is a simple closed curve, and R is completely determined. For example, in this part, if I have this A and B inside just the X line, X-axis, not in XY plane, then you don't have a choice. You have to go from A to B and just straight, right? And that's usually the curve we're talking about, just something like this. If you're in XY plane, if you have simple closed curve, then you don't have choice for R if R is completely determined. And then Green's theorem says, as we did for the line integral of a vector field, a gradient vector field, we can bring that inside to the integral by differentiating this function. Basically that's shorthand, and we fully understand what we mean by df in here. It's a shorthand of all this thing with missing this dt. But here we're doing the same thing, and we have to review the actual proof of the Green's theorem, but it's this wedge notation basically summarizes that. So we bring that dp p inside another integral called dp, q inside another integral, dq, and then you can bring this one out, performing this wedge operation, but that they're all proved rigorously in my earlier file. So that's the Green's theorem. So the line integral becomes this double integral, and this wedge product represent whenever there is a parameterization, it turns to this determinant, which is the signed part of the Jacobian. So we know this part. Now let me show you the Stokes theorem. F is going to be, now this is taking place in three-dimensional space. So here's x, y, z space, as I'm pointing out here. And C is going to be a curve. This is a curve in here. And this C you see down here is the same curve. As suppose these two things happening in the same x, y, z space. And this curve and that curve is exactly the same curve. But these two surfaces, S1 and S2, are different. S1 is a lot more surface area created, and S2 is kind of almost a disk, like a flat, but it's a slanted inside the hovering inside XYZ space. So although this has a boundary curve C, so I hope you recognize the C as a boundary. It's just like a little disk with a little wobbly end edges here. That edge is called a boundary simple closed curve. Just like this one here, if you look at the region R in xy plane, C serves as a boundary. This is taking place in the three-dimensional space, and S2 is more like this. So it's a boundary, but we're keeping the same boundary. You can create, you can put your hands in there, and suppose this is a elastic and a flexible dough, and then you put your hands in there, make it stretched out like this in S1, but keeping this C exactly the same. So more analogous to a fundamental theorem of line integrals. So let me show you that. So for example, like this, if I have A and B, and there are many ways to keep this A and B, but what happened in the middle could be various different possibilities. So boundary is the same, but C can be anything. The same thing like this. So here we're keeping the boundary exactly the same, but we can introduce this intermediate surface area, interior area, so called, and code totally different. So that's the situation. So what happens is that when we bring this one inside of the integral, another integral, so a little bit more complicated operations happening. So that was a curl. You probably had a chance to study this operation before. So if I have a vector field F, and this curl F is defined to be this one, Ry minus Qz, Pz minus Rx, and Qx minus Py. These are all the partials. And if this capital F happens to be the gradient vector field, and that's going to be Fx and Fy and Fz, by Clairaut's theorem, it turns out all of this thing is exactly the zero. So the curl was a natural thing that showed up to check if the given vector field is a gradient vector field of a scalar function or not, and the curl can be used to compute this one. If it is just a two-dimensional version, it was fairly simple, but if it is three-dimensional version, you have to check all this. What the Stokes theorem says, that if you have this line integral along the C, so this part here doesn't care about S1 and S2. This one doesn't know S1 and S2. It only knows the C part. If you calculate the work done by this force field along the C, that means how much of the contribution is coming from this force field when things are moving around this path of the C. You can bring that inside this PQR if you write it into a wedge product form or to just a differential one form. You can bring it inside another iterated integral and rearrange it as if it is a surface integral. It turns out and is arranged into this form. It's a curl F, which is a vector field we're looking at here against this ds, which is a surface integral of a vector field. So you can turn this line integral into a surface integral of a vector field, which is what you see kind of in a flat version in the Green's theorem. If you have a line integral, you can turn that into a flat double integral. You can view this as a surface integral with the z part missing. So that's the Stokes theorem. Bring the line integral inside the surface integral. Divergence theorem is that if you have a surface integral like this of a vector field, you can bring it inside the triple integral. Okay, so we'll see how this one arrives at here. It's a straightforward exterior algebra calculation. So I forgot to mention one thing about the orientation. When we start this left side integral, the line integral, it is orientation sensitive. If you think about the definition, it's orientation sensitive, although it's not sensitive to other parameterization. It's orientation sensitive. And a surface integral of a vector field also requires orientation of the surface here, normal vector sticking in which direction. So these two orientation has to be consistent to make this one work nicely. So that means if orientation of S1 is pointing upward like this, so put some more pictures in it. If this is our N, and if you put your thumb to it, and then the way your index and other fingers are pointing must be the orientation of the C. That's what we mean by having consistent orientation of surface here. When we actually calculate this, we use the orientation of the surface, namely the direction where the normal vector is pointing, and that should be consistent with the orientation for the curve we have in here, and that's the part of the statement. So now let me start with this line integral in this one form version. So if f has the component PQR, the line integral in three-dimensional space is going to be like this. Okay, again, C is now realized as the boundary of this S1, which is the one surface here, and but also the boundary of S2. Like the line integral case, this statement is valid for any surfaces. So the surface integral you're going to look at here does not depend on what surface you see here, but only depends on the boundary. So that PQR and this dx, dy, dz came from dr, the velocity vector. Now, next part I'm showing is that we're going to bring this each of this p dx inside another iterated integral. So you can turn this one into an actual integral in dt, and then you can bring it into another iterated integral using the parameterization of S1 and S2. So I'm assuming this sounds familiar if you study the proof of this Green's theorem and closely, and that exactly the same thing is happening. And calculation goes into this each of the part is quite repetitive method of this what we did in the Green's theorem. So I think using this wedge product exactly shows you what's happening to the details of the proof of this one, and rather we use this notation to nicely summarize all the details in a very nice way. So P is bringing inside the iterated integral, and Q and R, they're all coming in another integral in this form dp, dq, dr. These are the differentials of a scalar functions. We know that has to be px dx and py dy and pz dz. So they all is replaced by this one. So at this stage, this x and y are parameterized with the two variables, and this one here becomes the first column of a 2x2 matrix, determinant of a first column of a 2x2 matrix, and this one the second column. Same thing, this fills in the first column of 2x2 matrix there, that fills in the first column of a 2x2 matrix. Whenever there's the first column and second column is the same, you know the determinant is 0. So for example, if you see this dx and dx there in the first part, so I circle it there. If you combine these columns in that column, you know the determinant is going to be 0, right? And then qi and qy, dy, dy, and dz and dz. So that as you expand this determinant in this way, that's going to be 0. Alright, let me show you a little bit more. So what happened here, and then we're going to pair them up. So py and dy and dx, so that's what you see, and py, dy, wedge dx, that's what you see, and pz and dz dx. So I want you to look at each of the part if you have to pause the video and check that if all these things are correctly expanded. But you have to keep this order, which one comes left and right in the wedge product, because that's the columns of the determinant is sensitive to that. So if you expand that, and you have these things. So I want you to point out that some of them are similar, for example in dy dx there. So I put in the different color, you can see dx dy and dy dx and dx dz and dz dx and dz dy and dy dz. These are the same columns in different orders, so as we swap this, and you can have as a common factor. So if you put them together with the swapping the sign, then you arrive to the following part. Okay, for example, and if you look at dy dz, that's usually stated first. Dy dz, ry is exactly in front of dy dz, but this is dz dy, so if you swap the order, it picks up the negative symbol. So if you put them all together in this fashion, it becomes the following. This scalar times dy dz, which is the determinant of 2x2 matrix, and in the same way. Again, this is the surface integral of a vector field, which has these scalar components in the parentheses, over this surface sk, representing this could be this sk, this s1 and s2, whatever the crazy thing you can do in between, doesn't matter. The surface integral will be always the same as this line integral value, which only depend on the boundary of the surface. So it's very difficult to imagine what kind of vector field this is that we created. We named it curl, such that it has a property, just like the gradient vector field in gravitational vector field. It's not simple to understand the property, but it is happening in here. Okay, here's a final bit of the proof. As you can see, those were scalar coefficient in front of this wedge product dy, dz, and all that. So you can put it into this dot product form. Again, we can make only sense out of this when we look at this as some sort of quantity, which is the determinant, missing this parameter information. So it makes sense in that way. So that's the vector field created out of this PQR. That's original vector field. This new vector field. And again, remind you the name of this. This part here is called curl of the PQR. Okay, I wrote it there. So that part is called curl PQR multiplied by these determinants. And let's think about the meaning of this determinant again. So it actually turns out this is exactly RU cross RV if we put into a parameterization form. For example, if you have parameterization and the meaning of RU cross RV is a cross product of these two vectors. So the first component is missing the first column and determinant of YZ, and that's exactly what this part is. Second column is again XC and this determinant between this X columns and Z column, but we change the sign, so it's the same as swapping the sign, the order of these two things. And the last bit is X and Y, so we're filling an XY column. So if you do the parameterization and this turns exactly to the RU cross RV, our choice of a normal vector along with a parameterization. So this is exactly what we wanted. Namely, we show that this is a curl vector field, surface integral of a curl vector field. And another, again, the striking thing is that it doesn't matter how you close up that closed curve C with the surfaces. However you do it, that this value is going to be exactly the same. And try to and I want you to compare again, once again, with the fundamental theorem of line integral. If you have A and B, doesn't matter how you can connect those two using this curve, the line integral will be always the same. The same phenomenon is happening. It's a lot harder to understand. So in the part 3, we will look into more of these applications and the meaning of this interaction relationship between the curl and divergence and gradient and stuff like that. But here, let's focus on one of the example. It's an interesting example. So we have a vector field, which is given by xyz, xy there, x squared yz. And S is this surface of this cube, but missing the bottom part here. So we have all 4 sides and top. So we have 5 sides, but missing only the bottom here. So the C is working as a boundary. It's like that. And of course, if we're oriented outward, like this, that's the normal vector, by the surface integral of something. So that's oriented upward. Let me put that in. So I put that orientation in, so we have a meaning of surface integral, whatever the vector field is. So we're not going to actually consider the vector field, surface integral of this vector field. We're going to do the curl so that we can use this Stokes Theorem. So curl F is here. So we're going to, this is how you calculate it. You put this P and Q and R there and put this partial symbol over there and then do this operation as if these are cross product of two vectors. So missing that, delete the first column and do the cross product. Rather than multiplying, we actually operate the y operator there, so it's x squared z. And so I did the first part wrong. That should be x positive. So rather, if you do this one, you squared x, you get x squared z, and minus this one, which is 0. So this part's still correct after I change the sign. Then this middle part, and we change the sign. So I did this one first, and xy, and this one later, which is 2xyz. And the z part is going to be this part, so that's just y, and differentiate y over there is at xc, and subtracted it. So that's a curl. So we have a new vector field out of this, and this vector field has this interesting property that if you do the surface integral, and what could that be? And that's the question. So this is how it goes. It's quite cool. And I forgot to put these coordinates, so you have an idea of what kind of surface we're looking at. Here's the height 2, and then this all 2 by 2 cubes. So down there is a z coordinate -1. I put everywhere -1, and then corners are given by the 1s and -1s. So that's the cube we're looking at. So what the Stokes Theorem says is that as long as you keep the C and keep the same orientation, it doesn't matter if you do the surface integral over this crazy thing or just flat. As long as we have the same boundary, this surface integral, the surface integral of curl, will be exactly the same because it's the same line integral. We're not going to calculate line integral. We're going to do the surface integral, but with this simpler surface. It's the magic. That's the curl. Doesn't change anything. You can deal with a simpler surface, and then as long as we have the same boundary C here. So that's this S prime will be this flat surface that connects this boundary. So this is simply UV and Z is -1, where U and V varies from -1 to +1. So let me state that statement again. It's quite cool. So I just stated what I just said here. So S is this crazy shape, but S prime is a simple flat surface that has the same boundary to C. Then, and this curl, it does this magic, and this line integral, surface integral, this curl vector field is going to be exactly the same. So we just have to use this parameterization to go forward. So it goes like this. So we're changing the parameterization. So the vector field G, which is written here, which is a curl, and every x, y, and z are replaced by this parameterization. So for example, this one is u squared, z is -1, so that's why you see -u squared. This is u and v, and that's u and v with the -1, so altogether it's 3 times uv. That one's v minus, there's another minus there, so it's a v plus u. So that's the parameterized vector field dotted with the ru cross rv. That one is pointing upward, so that must be 0, 0, 1. And this is all now the double integral over this uv. uv is a rectangular region like this. So that's what this is. This is pretty cool. And here it is. If you actually multiply it out, you only pick up this v plus u part right there. And you can change it into iterated integral because R is a UV region and UV varies like that. So that's very simple calculation. So let me go back to the original problem. Sorry, the original problem like this. And again, the surface integral we're doing is not this vector field F. This strange vector field, this one here, that is given by these formulas. And if you do the surface integral of this vector field G and over these surface with the 5 sides is actually as simple as the surface integral over this bottom part, and with that the surface integral is a lot easier to calculate. So this example raises a very important question. So how do we know given vector field G in this way is a curl of something? If we know that this is a curl of something, and then we can just simplify the surface as any way you want, and then we can do this simpler surface integral than hard one like this. All right? So that's going to be part 3. Bye now.